Picture this. You're a U.S. Army engineer in 1972, staring at the burned-out hulk of an M113 armored personnel carrier. The diesel engine is toast, literally melted from an RPG hit in Vietnam. Your orders? Get this 28,000-pound beast moving again, fast. Your solution? Rip out what's left of the diesel and drop in something that shouldn't exist in military hardware, a gasoline V8. Not just any V8, a militarized derivative of the most feared racing engine in American history, the 426 Hemi. This is the untold story of how Chrysler's race-bred monster engine, banned from NASCAR for being too dominant, found a second life powering America's armored vehicles through some of the most hostile environments on Earth. An engine so overbuilt for racing that with minimal modifications, it could haul 14 tons of armor through sand, mud, and mountain passes while getting shot at. The 426 Hemi wasn't supposed to be a military engine. It was born in 1964 for one purpose: humiliate Ford at Daytona. Chrysler engineers started with a clean sheet design and created something unprecedented. The key innovation was the hemispherical combustion chamber, hence Hemi. This dome-shaped chamber allowed for massive valves, 2.25-inch intakes, and 1.94-inch exhausts, positioned opposite each other at optimal angles. The result was breathing capability that made other engines look asthmatic. The original race engine was rated at 425 horsepower, but that was a joke. On the dyno with proper tuning, these engines regularly punched out 550 to 600 horsepower. The compression ratio hit 12.5.1. The camshaft was so aggressive that the engine wouldn't idle below 2,000 RPM. It drank 103-octane fuel like a drunk sailor on shore leave. But here's where it gets interesting. The foundation of this engine, the block, the crank, the basic architecture, was massively overbuilt. Chrysler engineers, led by Tom Hoover, didn't just design it to win races, they designed it to win races while being beaten to death for 500 miles straight. The block featured cross-bolted main bearing caps. The crankshaft was forged from 4140 steel. The connecting rods were shot-peened and magnafluxed. This was aerospace-level engineering applied to a pushrod V8. In February 1964, the Hemi made its debut at Daytona. Richard Petty qualified at 174,418 mph, a full 5 mph faster than the competition. In the race, Hemis finished 1-2-3. NASCAR immediately banned it. Too dominant, too expensive, too much for the competition to handle. But Chrysler had spent millions developing this engine. They needed to recoup their investment somehow. Enter the street Hemi. From 1966 to 1971, Chrysler built approximately 11,000 street-legal 426 Hemis. These were detuned versions, only 10.25.1 compression, milder cam, cast-iron exhaust manifolds instead of headers. Still made 425 horsepower and 490 lb-ft of torque. Still the most powerful production engine you could buy. Insurance companies charged premiums that would make your eyes water. But enthusiasts didn't care. This was American muscle at its peak. Now, while muscle car enthusiasts were burning rubber on Woodward Avenue, the U.S. military had a problem. Their M113 armored personnel carriers, the workhorses of mechanized infantry, were powered by Detroit Diesel 6V53 engines. Good engines, reliable. But in Vietnam, they were taking hits. And when a diesel engine takes shrapnel or an RPG, it tends to catastrophically fail. Diesel fuel everywhere. Fires. Dead vehicles blocking convoy routes. The Army needed alternatives, fast replacement options. Something that could be sourced quickly, installed by field mechanics, and would reliably move 28,000 pounds of aluminum armor through jungle, desert, and mountain terrain. Some bright engineer, his name is lost to history, suggested they look at heavy-duty gasoline V8s. Specifically the Chrysler 440 and its bigger, meaner brother engines derived from the 426 Hemi architecture. Chrysler Industrial was already building marinized and industrial versions of their big block engines. These weren't the high-strung race engines. They were under-stressed, overbuilt workhorses designed to run at constant load for thousands of hours. The military version, designated the HT413 and later variants, shared the Hemi's basic architecture, but with crucial modifications. First, the compression was dropped to 8.51. This let it run on military-grade gasoline, basically 87-octane swill that barely qualified as fuel. The camshaft was designed for maximum torque between 2,800 and 2,800 RPM, right where an armored vehicle spends most of its time. The cooling system was upgraded with a massive radiator and dual electric fans capable of keeping the engine cool in 120-degree desert heat while barely moving. The oiling system got the full treatment: deep sump oil pan holding 9 quarts, high-volume pump, external oil cooler, full-flow filtration with bypass capability. This engine could run low on oil and keep going, critical when you're taking fire and can't stop to check dipsticks. But the real magic was in the durability modifications. The block was cast with extra thick cylinder walls, 0.625 inches, versus the standard 0.500. The head gaskets were military-spec multi-layer steel, not the composite garbage that failed on street engines. Every fastener was safety wired. Every gasket surface was machined to aerospace tolerances. The valve train, this is where the Hemi heritage really showed. Those massive valves that made the race engine breathe so well? In military trim, they provided unburstable reliability. The valve springs were deliberately undersprung, no valve float because the engine never saw above 3,500 RPM. The rocker arms were bushed, not needle-bearing, for longevity. The push rods were thicker than standard, designed to never bend even if the engine hydraulically locked from water ingestion. Testing was brutal. Chrysler's military division ran these engines at full load for 500 hours straight. Then they'd tear them down and measure everything. Bore wear, less than 0.01 inches. Bearing clearance increase, negligible. Cam lobe wear, unmeasurable. They'd rebuild them with the same parts and run another 500 hours. The torque output was staggering for a gasoline engine. While the street Hemi made peak torque at 4,000 RPM, the military variant peaked at 2,200 RPM, 521 lb-ft of twist. At 1,000 RPM just off idle, it was already making 400 lb-ft. This wasn't just an engine, it was a diesel alternative stump puller that happened to burn gasoline. Installation in the M113 required serious modification. The engine bay, designed for an inline-6 diesel, had to be restructured. The transmission, an Allison TX100, needed a new bell housing pattern. The cooling air intake had to be relocated. The exhaust system required complete redesign to route gases away from troop compartments, but it worked. Field reports from Vietnam were revealing. Units equipped with gasoline V8-powered M113s reported unexpected advantages. First, the gasoline engines started instantly in any weather. No glow plugs, no ether injection, just turn the key and boom, instant power. In ambush situations, those seconds mattered. Second, the gasoline V8s were quieter at idle than the diesels, better for stealth operations. Third, and most surprisingly, they were faster. The power-to-weight ratio improvement meant these modified M113s could hit 45 km/h versus the diesel's 38 km/h. In retrograde operations, military speak for getting the hell out, that extra speed saved lives. But the real test came in reliability. Military engines live horrible lives. They sit for months, then get started, and immediately run at full throttle. They ingest sand, water, and God knows what else. They run on contaminated fuel. They never get proper maintenance. They get shot at. The Hemi-derived military engines shrugged it off. There are documented cases of these engines running with multiple bullet holes in the block, still making enough power to limp back to base. One M113 in Cambodia took an RPG hit that destroyed the radiator and cooling system. The crew kept it running on just oil cooling for 18 miles back to Firebase. The engine seized solid when it finally stopped, but it got them home. The connecting rods tell the story best. The military specification called for rods that could withstand 12,000 pounds of tension without deformation. The Hemi-derived rods, carried over from the race program, were tested to 18,000 pounds. That's 50% over spec. This overbuilding philosophy permeated every component. The crankshaft could handle 1,100 lb-ft of torque, twice what the engine would ever produce. The main bearing caps were rated for 15,000 pounds of load. The head bolts were torqued to 105 lb-ft and sealed with aircraft-grade thread locker. The fuel system was completely reimagined for military use. No carburetor, too finicky for field conditions. Instead, they used a mechanical fuel injection system derived from diesel technology. No electronics to fail. No vacuum lines to crack. Just a cam-driven injection pump that metered fuel based on throttle position and engine speed. It couldn't match a carburetor for peak power, but it worked upside down, underwater, and full of sand. The ignition system was waterproof to submarine standards. The distributor was sealed with O-rings at every joint. The plug wires were military-spec silicone with redundant shielding. The coil was potted in epoxy and mounted in a shock-isolated bracket. You could submerge the entire engine compartment and it would fire right up once you surfaced. By 1975, over 2,000 M103s had been retrofitted with gasoline V8s. The program expanded to other vehicles. The M548 cargo carrier, the M106 mortar carrier, the M577 command post all received V8 transplants. Each application required unique modifications, but the basic engine remained unchanged. The same bottom end that won Daytona was now hauling ammunition through the Mekong Delta. The cost analysis was fascinating. A new Detroit diesel 6V53 cost the military $12,000 in 1973 dollars. A militarized Chrysler V8 cost $4,500. Replacement parts were available at any motor pool, often interchangeable with civilian truck engines. A field mechanic who'd never seen one before could rebuild it with basic tools. Try that with a diesel. Performance in extreme conditions exceeded all expectations. In Alaska, during winter exercises at -40 degrees, the gasoline engines started without auxiliary heating. The diesels required 2 hours of preheating. In Panama, during jungle operations, the V8s ran cooler than the diesels despite the humidity. In the Sinai Desert, during multinational peacekeeping operations, they survived sandstorms that killed other engines. But it wasn't all perfect. Fuel consumption was atrocious. A diesel M113 could run 300 miles on its internal tanks. A V8-powered version, 180 miles on a good day. In combat operations, this meant more fuel convoys, more vulnerability. The gasoline engines also required higher octane fuel than diesels, complicating logistics. And there was always the fire risk. Gasoline burns differently than diesel, more explosively. The engine's racing heritage showed in unexpected ways. The valve geometry, optimized for high RPM breathing on the track, provided exceptional engine braking capability in military applications. Descending mountain passes, drivers could drop 2 gears and let the engine compression slow 14 tons of armor without touching the brakes. The brake pads lasted 3 times longer than on diesel-equipped vehicles. The forged internals had another advantage. They were virtually indestructible under military loads. While the race engines saw 7,000 RPM and extreme stress for hours, the military versions loafed along at 2,500 RPM. It was like using a sledgehammer to drive finishing nails. Massive overkill, but it never broke. Maintenance intervals stretched beyond belief. The original specification called for oil changes every 100 operating hours. Field experience showed the engines could run 500 hours on the same oil with no measurable wear increase. The air filters, massive paper elements the size of office wastebaskets, could ingest pounds of sand before restricting flow. The spark plugs, military spec with gold palladium electrodes, lasted 2,000 hours. The human element mattered too. Crew members loved these engines. They had personality. The V8 Rumble was distinctly American, a morale booster in foreign lands. Drivers who'd grown up working on muscle cars understood these engines intuitively. The throttle response was immediate, not the laggy response of turbocharged diesels. In combat, when split seconds mattered, that instantaneous power could mean survival. There were failures, of course. Early versions suffered from vapor lock in extreme heat until the fuel system was fully pressurized. The exhaust manifolds, cast iron like the street versions, would crack under extreme thermal cycling. The solution? Tubular stainless steel headers like race cars used, but thicker walled. Problem solved. The military Hemi program officially ended in 1981, replaced by more modern diesel engines with better fuel economy and lower infrared signatures. But thousands of these engines remained in service through Desert Storm. Some are still running today in allied nations' armies. Egypt, Israel, Jordan, they all received M113s with American V8 power. The technology transfer went both ways. Lessons learned from military applications improved civilian engines. The high-temperature valve seal materials developed for desert operations appeared in civilian trucks. The waterproofing techniques influenced marine engine design. The ultra-durable bottom-end specifications became the blueprint for industrial engines that powered generators, pumps, and oil field equipment. Looking back, the marriage of racing technology and military requirements seems obvious. Both demanded absolute reliability under extreme conditions. Both required maximum power from minimum weight. Both pushed materials and engineering to their limits. The 426 Hemi was born to dominate NASCAR, but its true legacy might be the thousands of soldiers it brought home safely. Consider the engineering philosophy. Build it twice as strong as necessary, then add 50%. This wasn't elegant engineering, it was brute force reliability. Every component was overbuilt because in racing, failure meant losing a race. In combat, failure meant losing lives. The engineers who designed the Hemi for Daytona had no idea they were creating an architecture that would save soldiers in Southeast Asian jungles. The street Hemi guys, the ones paying crazy insurance premiums to own 425 horsepower of barely streetable muscle, they were driving a detuned version of a race engine. But the military was running an understressed version of that same architecture, same basic DNA, completely different expression. One built to scream at 7,000 RPM, the other to grunt along at 2,000 RPM for thousands of hours. Modern military engines are technological marvels, computer-controlled, multi-fuel capable, thermally efficient, but they lack the mechanical simplicity of those Hemi-derived V8s. You can't fix a common rail injection system with a hammer and determination. You can't troubleshoot multiplexed electronics in a sandstorm. Sometimes simpler is better, especially when people are shooting at you. The last military V8s were retired from U.S. service in 1995, but their influence continues. The design philosophy, overbuilt, understressed, field-maintainable, influences military procurement to this day. When the Army evaluates new power plants, they still reference the reliability statistics from those Chrysler V8s. It set a standard that modern engines struggle to match. Today, surviving examples are museum pieces. The Army Transportation Museum at Fort Eustis has a cutaway display showing the engine's internals. You can see those massive valves, the forged crank, the fire-ringed head gaskets. It looks like a race engine that got drafted, which essentially it was. The story comes full circle in unexpected ways. Restoration shops specializing in vintage military vehicles now source parts from muscle car suppliers. That NOS 426 Hemi rod, bearing on eBay? It might end up in a restored M1 or 13 in someone's collection. The same crane camshaft that would have gone in a street racer's Plymouth might end up in a military commemoration vehicle. What does this tell us about American engineering? That sometimes the best solutions come from unexpected places. That racing development, often dismissed as frivolous, creates technologies with real-world applications. That building something too good for its intended purpose might make it perfect for something else entirely. The 426 Hemi started as a racing monster, but its military cousin powered armored beasts with the same fury. Same chromosomes, different expression. One conquered racetracks, the other conquered battlefields. Both are legends in their own right. Both showcase American engineering at its most excessive, most overbuilt, most gloriously uncompromising. The next time you see a restored muscle car with a 426 Hemi rumbling under the hood, remember that its military brother saved lives on the other side of the world. Racing technology and military requirements converging in cast iron and forged steel, horsepower, with a purpose beyond the quarter mile. What's the most unexpected military application of civilian technology you've ever encountered? Drop your stories in the comments. And if you want more deep dives into the engineering that changed history, both on the track and the battlefield, make sure you're subscribed. Until next time, keep those engines running, whether they're heading to the drag strip or coming home from deployment.